Is Sergey Klimenko, and the title is The Detection of Gravitational Waves from Quark Lab Supernovae.
This is the point, right? Okay. Yeah, thank you. Do I have 30 minutes or less? Okay. So I'm going to talk about detection problem. And here I would like to go under the hood a little bit so we can understand better the challenges and limitations here. And how to move. How about now? Okay, and this is a plot which you all know, and basically it's showing all three important messengers from Quark Lab Supernova. And the main, we had a lot of talks about this, and the main takeout probably is that we can detect optical to cosmological distances, but it's hard to interpret this physics, and particularly to project it back to the proto-neutron star. Neutrinos are great. We can see, the neutrinos within seconds from the core bounds. And the detector problem is well worked out, and we just need to scale up our detectors. And for gravitational waves, we have current detectors. We expect to see more third generation detectors. But the main message is that detectors are complicated. Search algorithms are mysterious, and we hope that AI will save us all. And here I would like kind of to talk about this part and say that actually from the detection point of view, the detectors are simple and can demystify the search algorithms. So here is kind of the current state of the art in the field. This is our best limit here from the nearby Quark Lab Supernova. And by looking at these sources here, this BBH and BNS, and these Quark Lab's simulations here, we see what the scale of the problem. So we need to go down to very, very weak signals. And of course, there are different projections for the O5 run shown here. And also the 3G detector, they expect to have at least 100 times in energy improvement. And we hope to detect some of the weakest signals here in this group of events. And of course, we have sources. This is the detection is greatly depends on what kind of models we expect. And the models are shown here, kind of realistic, optimistic, and enthusiastic. And we should actually shoot for realistic models. So let's get back to the detectors. And here we have, we already know that the detector responses can be written as the product of the antenna patterns and the gravitational wave amplitudes H here. So it means that this F plus and F cross should be multiplied by this vector. And then we have a detector response for detector 1. And so on, we can continue doing this for other detectors and get what we call the response vector. If we totally ignore noise, then for a sampled detector output, this vector here will represent the response of the entire network of detectors. And then, of course, the signal can be represented. This would be the network response to gravitational signal, and these are gravitational wave amplitudes, which are coming to us from space. So this is essentially, we can boil down, the all detection problem to 3 vectors. 2 of them are shown here, and it's convenient to work with white-end detector response because the dynamic range of the noise is huge. And here we just normalize the antenna patterns by the spectral density, spectral amplitude of the noise. And then these 2 vectors, they represent what we call the network plane. Okay. And our gravitational wave signal, by definition, should live in this plane, this yellow vector xi. All the other directions are not really important at this point, but if we add noise, then we get the data vector x, which is we recording from the detector. And of course, we also can, because we have this polarization angle, which is essentially defining how we define polarization H plus and H cross in the wave frame, we can always rotate these vectors to make this orthogonal. And the norms of these two vectors actually define two important parameters. The first one is just simply what we call the acceptance. This is the sensitivity of gravitational wave detectors with respect to omnidirectional network. You see that it ranges from 1 to 0. And we see these famous red spots, which are corresponding to areas of high sensitivity, angular sensitivity for LIGO detectors. And these blue spots, which are corresponding to a low sensitivity of LIGO detectors. So you need really strong signal to be detected here. And also, this plot is showing, the ratio of norm of F plus divided by norm of F cross divided by norm of F plus. And it's essentially showing what is the fraction of SNR goes is coming from the H plus H cross polarization. And here we can see that if you look at this point, then essentially H cross is not adding anything to the SNR of the detected signal. And it's only the red spot, we have equal sensitivity to the plus and cross polarizations. But unfortunately, this spot's happening at these directions, where the total network sensitivity is low. And therefore, it's pretty much, useless. So if you look now at the future detectors, Cosmic Explorer and Star Telescope, then the situation is much better. And here, it doesn't matter if you have 6 or 3 detectors at ET, we can see that, we are now covering sky, much better than for LIGO detectors only. And it's actually beneficial for the core collapse supernova because now we have less chances to miss our signal. But also, you can see that we can measure quite well also the cross polarization, and still we have some blind spots for the cross polarization, but not as big as for the Livingston and Hanford detector. So the main message here is that we have improvement in the strain sensitivity by factor of 10. But also because of the network configuration, we will have another factor, it's like square root of 2.5, which is coming from the network configuration. So how we can measure gravitational wave polarizations? If we just simply look at this detector network responses vectors xi here, and of course, we have sample data. It means that we have a bunch of vectors. And after applying some simple magic transform, we actually can see the polarization state of the wave in the network plane. And here you can see if you have a linear polarization, then we actually can introduce this vector xi tilde. It's 90-degree phase shifted vector of vector xi. So it's not something we can easily get it. But now, if we look at, we have wave with linear polarization, then this xi tilde is equal to 0, and all the vectors are aligned along some direction, characterized by this angle psi. And of course, this can take random direction for different waves coming to us from space. This would be circular polarization, and this is elliptical. So we can, if we don't have noise, and we can do kind of very easy data analysis by looking at finding what is the polarization of the incoming wave. Of course, the reality is that we have noise, and that means that this pattern is dispersed, and also the network is not letting us to find this pattern very well. So this is the problem with capturing the polarization. So if we are sitting in this spot here, where we have H plus and H cross sensitivity about the same, then we see the whole wave. This would be the response, okay? And it means that we see the whole polarization pattern here. So if you are at this spot, then the length of the F cross vector is close to 0. It means that by definition, the response should be always aligned along the F plus. It means that any gravitational wave with any polarization coming to HL network will look like this one. So we are totally losing information about the polarization state. Now let's add the detector noise. And there are two types of noise here. This is fundamental noises, which we described before. I will not go to details. The main point here that this fundamental noise is kind of introduces noise bubble, which is we have these vectors all spherically distributed, with some RMS distribution of this, basically, of this noise here. But also we have the called glitches. These are instrumental or environmental artifacts, which can have pretty much any amplitude. And you can see here that this is pretty outdated plot from first detection. But once the network sensitivity, the noise is decreasing, actually we have more and more and more strong glitches because we discover new sources of glitches. And this is here, you see that this is SNR, this is rate, and this is the magnitude of the first event which was observed by LIGO. And it's impossible pretty much to have a confident detection if you have just one detector. So we need at least two, preferably more detectors. So we now can distinguish between noise, glitches, and the gravitational wave signal. Now let's get back to the signal identification problem. Basically, how we do the searches. And here, we can first look at the match filter. Again, we have this network plane defined by these two vectors. This is gravitational wave response. And we have, this magic wand here, which is our template. And of course, template is characterized by many samples. So it means that we have, all these vectors sticking in different directions. And we need to find the right template, which actually will match the corresponding gravitational wave signal. And this can be done efficiently by calculating this dot product. And obviously, we have, this beautiful method because in this way, just maximizing, this dot product, we can find the best matching template. And if, for example, the magnitude of this this template amplitude is equal to 0, we totally exclude, all irrelevant noise. And this is the way how we can recover signals with power in each individual pixel or data set, the data sample, which is much less than underlying detector noise. Now we remove this vector here, so we don't have template. And we end up only with the detector response here. We don't know this yellow vector. We only have that one. And now we start to scratch our head what to do in this case. And the first what comes to mind is, okay, this vector here, data vector, may have amplitude significant, magnitude significantly larger than the noise. So let's first identify, all these cases. And this methodology is called excess power. So essentially, we are looking at all the data vectors which are inconsistent with the detector noise. And it requires that somehow this power should be greater than the power of the underlying noise. And then once we identified all this vector, we need to find the solution of the inverse problem. And this is done with the maximum likelihood method. And in this particular case, Michele discussed this, but if you just simply take a simple maximum likelihood problem solution, it all boils down to finding this projection here. In reality, we can do better. I will not go into the details here, but we can find, basically best approximation for this vector Xi, and this is our reconstruction. And how we find, these vectors which are relevant, so it's not noise. And this is where time frequency analysis comes to rescue. And this is kind of, in a nutshell, what we actually do. we start, with these atomic waveforms, which are called wavelets. Atomic in the sense that they have minimal time frequency uncertainty. So if you calculate the typical width in time, typical width in frequency, these integrals here, then the product actually it should be greater than 1/2. This is a classical actually results from quantum mechanics that if you have a wave packet, if you shrink it in one direction, it should stretch in the other. And the point is very simple. You have this atomic waveform. It's an example, Gabor wavelets, for example, it's signed Gaussian wave in some window envelope. And it just simply adjusts the parameters of this wave. So it's sitting somewhere here on the time frequency plane. And then you estimate the power at this point by simply looking at the overlap of this waveform with the data. And then you can put, whatever number of waveforms on this time frequency plane, hoping to find the best estimation of power. And of course, you cannot localize it infinitely well because of this limitation. Now, we can have different ways how we place our waveforms on this time frequency plane. And this is a classical wavelet. It has good time resolution here at high frequency and bad timing resolution at low frequency. This is what we call WDM wavelet, which has uniform tiling of the plane. And also you can make these waveforms totally orthogonal to each other, and that it forms orthonormal basis, which is good sometimes for the analysis. Or you can simply put, whatever number of waveforms in here with any density, like Q transform, and also try to estimate the power spectral density. And this is what we can do. And immediately we run into this problem. So here we just use Gabor wavelets, and we kind of very densely put it on the time frequency plane. And they have different duration of the envelope, 16 milliseconds, and so on. And there are 4 types of signals here, some kind of lines, chirp, and sine Gaussian wave. And it's clear that this resolution is not good for detecting any of them. This is much better for sine Gaussian. This is getting better for this slowly varying noise. Okay, this is actually good to detect the merger. But then when we change the resolution, we find out that there is no one optimal resolution for all of them. And again, we start to scratch our head and think what we do with this. And the solution is obvious. We just simply pick up the maximum amplitude from each resolution. Okay. Basically, if you detect at this particular time frequency location, we find the best power from this resolution, we just simply pick it up. And we can do this. And this is what we get. Indeed, we see now all the signals, but on the top of that, we also see this strange kind of fake power. This is called spectral leakage. This is temporal leakage. And therefore, if you now try to identify all these vectors which are sticking out of the noise, you see that we start to pick up a lot of irrelevant time frequency locations which are affected by this spectral leakage. And so this is pretty much algorithms which we used before the O4. They are all affected by this. And this was a motivation to develop a new time frequency transform, which is called WaveScan. And it actually allows to pick up not the maximum resolution, but actually the optimal resolution by simply looking at the overlap integrals of the corresponding wavelets. And this is what we get. So now, basically, we can kill the spectral leakage. We can see all the signals clearly on this time frequency plot. And now we are ready to set the threshold on the power and pick up all these signals here. And the price which we pay here is that now at each time frequency location, like here or here, the resolution of wavelet functions which is used here is different. So this is how it looks like for famous signals. This is the first detection over here. This kind of lizard, it's result of the Q-transform, basically how we can visualize it with Q-transform. This is how the wavescan sees it. And this is the famous neutron star event with this depressing glitch over here, which gave us a lot of problems. But you can see here that all this power of the glitch is actually fake. It's an artifact of the transform. And if now we look at how it looks like, the power distribution with the wavescan, we see that the main glitch is actually very, very narrow. And this allows to remove it efficiently without affecting our signal. Now let's get back to the algorithm, how we do the search. Of course, we need to produce, all these time frequency maps, like in this case for 2 detectors. And then by looking at the pixel in this map and the corresponding pixel in that map, we need to make a decision. Do we take this pixel into the analysis or not? And this can be done based on 2 properties. Basically, we can calculate the excess power. It is a sum of power in 2 maps. Or we can calculate the cross power, the product of 2 powers. And it's not that simple because there is time of flight between the detectors. And it means that instead of just producing these 2 maps, we need to produce like thousands of them to account for possible time of flight and recalculate the amplitudes for any possible time of flight. To make things more complicated, actually, we also need to reconstruct point in the sky. And usually it requires to search over like hundreds of thousands of sky locations. And this is what makes algorithm very complex. But the benefits of this that now in this case, so we do not use any assumptions of the underlying signal. And this is how, these signals like the first detection, also very massive event, GW190521 was detected. So it means that once we identify the excess power and the cross power here, and this is obtained for the network of detectors, actually there is another problem that the statistical property of this statistic is actually quite horrible because the detector noise is changing, the detectors are breathing. So it means that the statistical distribution of these quantities is changing. And it's hard to put a threshold. You don't know at any given moment what the threshold should be. But it's possible to solve it by converting this to universal statistic. Basically, we have some generic gamma distribution, and it can be converted to half normal distribution using simple equations. And this is what you get. So this is Gaussian peak corresponding to the fundamental detector noise. The excess power statistics shown in black, and you can see the tail, these are glitches, and the cross power statistics shown in green. And you now see the utility of the cross power statistic. It's much less affected by glitches. But nevertheless, in our analysis, we select all the data points where the sum of this excess and cross power is actually greater than some threshold. And this is because we still want to keep our glitches in the data. And then when you select this data, you get this kind of plot. This is the previous BNS signal. You can see a bunch of clusters here. This is these are not individual pixels, they're a group of pixels. And this is Gaussian noise, a glitch is here, and we see a BNS signal, in this region. So at this point, it's not possible to do analysis because there are too many clusters on the time frequency plane. And therefore, we need to select it in some way, basically to get rid of most of these Gaussian clusters by using some cluster statistics, shown here. And this can be done efficiently. We can construct, some statistic which is specifically designed to kill Gaussian noise. And it has very nice distribution, like exponential, and we start to see non-stationary events. In this case, it could be gravitational waves, could be glitches, and just simply pick up, these events here, and we can clean up our time frequency map quite well. basically reducing the rate of these events by like an order of thousands. After that, we can use a statistic which now is killing glitches. And this is how the time frequency map looks after that. So we still see, some stubborn cluster here coming from Gaussian noise, but now we have all these clusters coming from BNS signal, and we see that it's very fractured. So we need to collect all this power again. So we kind of will increase the signal to noise ratio for our detection. And this is very important for core collapse supernova signals simply because they span very large time frequency area, and they are fractured like this. Okay, so this is of course simulation, but this is Hanford, this is Livingston, and this is event, which after all we can identify. And you can see that this is this particular signal, C15 3D, with a SNR of 29. And what is requiring, efficient defragmentation? Okay. All right. So and here now once we identify the event, we go to reconstruction, and we can find the scale location, and you can see here that this is a simulated event. And actually, this kind of location is not very useful in the case when we have optical counterpart, because if it spans, time duration of day, then we always can find trigger which is actually overlapping with this error regions, and also can reconstruct the waveforms. So what is limiting core collapse supernova detection? These injections at different distance. Here we can detect very well the core collapse supernova events, but when we reduce SNR, with injected SNR of 24, we just see one speck here, and essentially we cannot say anything. Probably we can say that probably there is signal here, but we cannot say if it's supernova or not. And the problem is in how we select our pixels and our clusters as well. And here what we can do, instead of excess power, we can use the cross correlation, which is shown here. And essentially we need to calculate these products here of the amplitudes and integrate them over some region in the time frequency plane. And then if you do this, we get, instead of event like this, for the same event, we reconstruct something what is reminding, looking like supernova in this case. The price for this is a complexity. It essentially, we need to manipulate much more data, which is a limiting factor here. It's for different versions of the coherent Weber's algorithm using excess power, cross power, and cross correlation. Every time, when we move, for example, to this version, it's significantly slower and requires, yeah. Okay, but we can use what we call the pattern recognition. Here the injections at different SNR, and you can see that actually we can see the pattern for gravitational signal, which slowly dissolving into the noise. And this can be used, if you know that this pattern is robust, we can actually distinguish it from the glitches. Okay. And this is my summary. So that we actually, right now, we can detect signals like this out to maybe 3 kPa, and we can improve it a little bit. But this is pretty much what we can do right now in O5. Hopefully, we can deploy, the algorithm, which is dedicated algorithm to search for core collapse supernova. And this is useful because, we want to produce this in low latency. And if we have a supernova alert, then it can be used, for telescopes to follow up the event. And the future detectors, they have much better sensitivity, and hopefully these realistic signals will be detected out to 30, 50 kPa, and optimistic signals can be detected out to 1 megaparsec. Thank you.
Maybe one short question. Any questions?
On your previous slides, where you were discussing the pattern recognition issue, what's the plan? I mean, what do you have in mind to which kind of feature you want to use to?
This is where we need some input from modelers because I was looking at previous presentation by Tony, and I was actually clear that 9.6 solar mass simulation is very different from the other. So, and we cannot really say that this kind of pattern here is a unique property of core collapse supernova. But if we can limit the range of these morphologies, it actually would be very useful for the analysis. Because here we don't need to know what is exact waveform and so on. We just need a very characteristic feature of the signal. And if indeed, this is kind of a robust feature, then it means that we can distinguish it from a large class of glitches and reduce the false alarm rate quite a bit. This is not something new, because we already have used this technology for VBH detection, where we have this characteristic chirp signal. Okay, and this is actually where the machine learning actually can be very useful, because it allows to solve this classification problem. But to be able to do this, we need a very robust feature. Okay.
Why not using the universal relations that we were discussing earlier in Alex and universal relation is giving the frequency of the, because you're talking about the high frequency mode, this feature.
Yeah, it would be great, but if, for example, like for this 9.6 simulation, it does not really have this feature, or it has, this, but it's very low SNR. And the most of the signal is actually here, somewhere here. Okay, and therefore, if indeed this is true, it looks like that, then it means that we need kind of to increase this class of morphologies and see, if, but why then we make this class less efficient, the pattern recognition will be.
Okay, then please ask the remaining question in the lunchtime. And I would like to thank all three presenters in this session.